All right, this video is going to talk about complex numbers and how we can represent them in what we call trig form, kind of writing them in a slightly different way. Normally we write complex numbers in what we call standard form, right? They've got two parts. We've got the real part, so over here in our example, that's a 3. And then we've got the imaginary part, so over here b, or right here would be 2i, right? So 2 times I, that's an imaginary part, because again, I is that square root, right? I equaling the square root of -1. So we can plot these though. We can kind of imagine this in a graph, which is going to help us when we start to think about, again, doing this in sort of a trigonometric form, writing it in a different way. The complex plane basically just says our real axis, so the axis from sort of left to right here. Normally the x-axis is going to be the sort of a number line, right? It's going to be where we represent that 3, so I would go 3 units to the right. And then the 2i, well, the up and down, or the vertical axis, right, is going to be our imaginary axis I. So if I wanted to plot this point, well, very simply, all I would have to do, right, is draw a to the right, right? I'm going to go 3 units to the right, and then b units upwards, right? So a would represent that length horizontally, b would represent the length vertically, and what we would call the absolute value, right, or the absolute value of our complex number would essentially be the length here of our green line. Okay? Absolute value meaning distance from 0. So notice we've got those absolute value brackets. But basically that point, right, just that black point, is the point 3 plus 2i. Again, its absolute value would be the distance, and in order to get that distance, well, basically it's just a right triangle, so we can just say a squared plus b squared should equal, right, our c squared, or basically our absolute value of z here, z being our complex number. And if that's the case, well, basically that's going to represent r for us very simply, if we think of that as a radius, right? So again, if we took our numbers, right, and we said the square root of 3 squared plus 2 squared, the square root of 9 plus 4 is the square root of 13, and you'll notice I've represented that radius, that distance from the center. Basically our point just became this black dot that's exactly root 13 units from the middle, and all I really need to know now is what this direction angle would be. I don't have to measure A and B, right, measuring rectangular sort of, or right and up. I can actually say, well, let's go out, directly out to our circle, root 13, right? And I'm just going to know, okay, at what angle should I travel? And then travel that distance out. And I should end up, again, at our black point that's just 3 plus 2i, right? Well, in order to get the direction angle of z, we'll realize that, again, we know a and b, we know 3 and 2. So if we know the opposite and the adjacent, well, let's go ahead and find a tangent. So the tangent of theta for point z here, right, so we have a little sub z there, but the tangent of theta will be equal to b over a. So we can say that the inverse tangent, right, so inverse tangent of, for us, 2 over 3, right, will end up being what we're really looking for, right? And that will give us the direction angle, right, theta, our purple line here, that theta in our triangle. Well, in that case, let's go ahead and we'll type that into our calculator. So just give me 1 second here. Open up that calculator. Remember to take inverse tangents. Don't forget to hit second there. Of 2/3 gives me a 33.690. 33.690 degrees will be our direction angle. And that makes sense. We're up in quadrant 1 there. So finally, how do we write this in trig form? Again, if you're familiar with vectors, this is going to be a very similar form to that. Let's draw a little line there to separate. Basically, you can just take your radius, right, your distance here, multiplied by the cosine plus I sine, right, of our angle, with our direction angles mixed in there, right? Looks very similar, again, to how we wrote a trig form of a vector. Our magnitude, or what we this time are calling the radius, would be multiplied by the cosine, telling me that's the horizontal piece, the real part. And then the sine, again, opposite on a unit circle, the sine would be the vertical, so the sine times the imaginary part, right? Forcing that to go up and down. There is a sort of shortcut way of writing this. It's familiar notation. Since we're going to use the same angle both times, you can also shortcut this. Instead of saying cosine plus I sine, you can write that as CIS. So again, R times CIS, meaning cosine plus I sine of our direction angle, right? Our angle would be in there twice. So let's go ahead and write down our formula. Let's go ahead and use the shortcut method. We would just say root 13 CIS, right? Cosine plus I sine of our angle, 690 on there. And that's how we would write an imaginary number, right? A complex number in trigonometric form. Let's go ahead and try that a couple of times. First of all, we're going to convert into trig form, and then we'll show you very quickly how you can convert back out of trig form. And it's a pretty easy process. But let's start with this example over here at the left. First thing I would always recommend is just draw a picture. Let's get an idea where this thing is going to be. So we're going -1 unit to the left, and then we're going to go up root 3 units. So again, we're going to be extending essentially out here. Now realize, technically we're just plotting a point, but to know that line, that's sort of helpful, right? That's going to be that distance. So I don't mind if you draw that line. It's just sort of helpful there. But realize that we're only really plotting that point. So technically, we should really just say, there's what we're looking for. But again, in order to represent what we want, we kind of want to picture this triangle, right? Because we need to find the length here and we need to find that angle. So let's do our length. Again, if this is number, we'll say, let's just call this, Z again, not a bad name for it there. What we want to find is the absolute value of Z. We want to find how far is it from 0? What's the length of that hypotenuse? So square root of -1 squared plus root 3 squared, basically square root of, that'll be 1 plus 3 is 4, and we get a nice length of 2 there. Okay? So that looks pretty good as far as the absolute value goes, right? The absolute value of a complex number, just the distance from 0. Then we can say inverse tangent, right, of b over a, so root 3 over -1. Now you might be fairly familiar with those numbers. Root 3 and -1 definitely sounds like a 30, 60, 90 triangle. If we're 1 unit here and we're root 3 units on this side, I'm thinking that looks like a 120-degree angle, right? So you can go ahead and pop it in the calculator. Realize that it's probably going to give you -60 though, right? It's probably going to put you down here. Don't forget to add 180. Definitely looks like we're at about a 120-degree angle there though. So then we can write our trig form. Again, we're going to say the magnitude or the length of that line, the absolute value, times the cosine at 120, plus I, the sine at 120, or basically CIS, cosine plus I sine, of 120 degrees. Now to convert out of standard form, we kind of have to just type this in. But first I need to re-represent this. Again, I'm going to need these two separate parts. So that CIS notation is not as helpful now. So I'm going to go ahead and say 5 times the cosine at 135 plus 5I, the sine, at 135 degrees. Which the nice part is, again, those are just 45-degree angles, right? Or a 45-degree angle over into quadrant 2 here, right? So basically, we can say that's 5 times cosine being negative in that quadrant, negative root 2 over 2, plus 5I, right? Sine is positive in quadrant 2 though, so positive root 2 over 2. So if we wanted to stay exact, basically we just got -5 root 2 over 2 plus 5I root 2 all over 2. Now you could also pop that directly in the calculator. It just depends on what the directions say. So 5 times the cosine of 135 degrees would have been a -3.536. And again, you could double check and make sure that that lines up with, again, that fraction we just got, right? plus, well, I'm guessing 5 root 2 over 2 is not going to be any different, only this time we're positive. So 3.536i, right? I can't add the two of them together purely because of that I is imaginary. But again, probably more likely, let's go ahead and keep that exact, so that sounds like a better answer. And if you have any questions about how to convert, again, either a complex number into trig form or convert trig form back to a complex, standard form number, make sure you talk to your teacher. Otherwise, have a great day.